In this video, we are learning about the example question 7.8. In the previous one, we talked about how the equilibrium constant can be used to calculate the equilibrium concentration. In this one, we're talking about this example problem. 13.8 grams of N2O4, 13.8 grams of N2O4 was placed in a 1 liter reaction vessel at 400 Kelvin and allowed to attain equilibrium. Now, the total pressure at equilibrium was found to be 9.15 bar. Calculate Kc, Kp, and the partial pressure at equilibrium. Now, we need to calculate the partial pressures of these substances. We also need to calculate Kc as well as Kp. Now, let's start at the beginning of this. Okay, now, how do we get from this question to actually calculating a value that we can figure out? Now, since we've been given the total pressure, right? Maybe we can use the total pressure will be equal to the sum of partial pressures, right? And this we can figure out, from this, we can say that we just need to figure out the initial pressure in the system because we've been given the pressure at equilibrium. So yeah, I started the problem with assuming that this was the initial pressure and started doing the whole X calculation. But because this is the 9.5 bar is at equilibrium, this is not the initial total pressure. So we have been given something, though. We've been given N2O4. So we've been given the mass of N2O4, which is equal to this 13.8 grams. Okay, we've been given the volume of the reaction is 1 liter. And we've also been given the temperature. So do you think maybe from this we can calculate the pressure? So that is PV equals to nRT. So pressure equals to nRT divided by V, where N is the number of moles, which we can calculate from the mass. So mass, N equals to mass by molar mass. So molar mass for N2O4, that is 14 2s are plus 16 4s are. That is, molar mass for this is 92 grams per mole. And the mass given is 13.8 divided by 92 grams per mole. Oh, sorry, grams. And this gives us 0.15 mole. Now we have R, which is the universal gas constant, which is 0.083 bar liter per mole per Kelvin. So let's substitute all the values. So 0.15 mole into R, that is 0.083 bar liter per mole per Kelvin into T, which is temperature, which is 400 Kelvin. The best part is they've given the temperature to us in Kelvin, so we don't have to convert it from Celsius. And then divided by 1 liter. So L gets cancelled. Let's talk about the units first. Moles, Kelvin, and then we're left with bar, which is what we want, the pressure. And now this on simplification gives us 4.98 bar. So this is the initial pressure. So we calculated the initial pressure of the reaction from the mass of the reactant and the volume and the temperature the reaction is at. So let's write down the chemical reaction over here. N2O4 is in equilibrium with 2NO2. So the initial pressure is 4.98 for N2O4 and it'll be 0 for NO2. And let's assume that X is the decrease. X is the decrease of pressure as the reaction, pressure of N2O4 as the reaction approaches equilibrium. Okay, so X is the decrease of pressure as of N2O4 as the reaction is approaching the equilibrium. So at equilibrium, our pressure of N2O4 is going to be 4.98 minus X. On the other hand, for NO2 is going to be 2x because we use the stoichiometric coefficient. So 2x bar. And so remember, we've been given the total pressure at equilibrium. So the total pressure, that is P total, will be equal to P of N2O4 plus P of NO2, right? So, which is 9.15 equals to 4.98 minus X plus 2X. Let me just scroll down a bit. So X equals to 9.15 minus, actually, let me step. So 9.515 equals to 4.98 minus, plus X. So X will be equal to 9.15 minus 4.98. And when we simplify this, we get 4.17 bar. So the pressure, that is X, is going to be equal to 4.17 bar. Now we can calculate the pressure of NO2. So PN2O4 will be equal to 4.98 minus 4.17, which is equals to 0.81 bar. We're basically substituting the value of X. PNO2 will be equal to 2 into 4.17, which is equal to 8.34 bar. Now we've gotten the partial pressures, and from this we can, so this was one of the questions where we had to calculate the partial pressures, which we got. The next one is we need to calculate the value of Kp. Now from the chemical equation, no, sorry, I had the thing in both places. Anyways, for this equation, we can say that concentration of NO2 to the power 2 divided by, oh, sorry, Kp, right? I got so used to talking about Kc. So PNO2 square divided by PN2O4, which is equal to, we've calculated them both, that is 0.81 for PN2O4 and 8.34 for PNO2. So I'm just going to write those values over here. So 8.34 square divided by 0.81. And this is equal to 85.87. So we were able to calculate the value of Kp. Now we need to calculate the value of Kc. Basically, you can just substitute. So we know the relation between Kp and Kc. You actually learned this in a previous video. So Kp and Kc, Kp equals to Kc into RT to the power 1, sorry, delta N. That is the total difference in number of moles, which is 1 minus 2, which is equal to 1. Now, Kp is equal to 85.8. Okay, let me do this way. Okay, so Kp equals to 85.87. R, which is the constant, equals to 0.083. T is the temperature, that is 400 Kelvin. Delta N will be equal to the product minus the reactant. So the number of moles of product is 2 minus 1, that is equal to 1. We are going to substitute it in the above equation. So 85.87 equals to Kc into 0.083 into 400 to the power 1. Now, when you simplify this equation, you get that Kc equals to 2.586, and this can also be written as 2.6. And that is how you solve this question. So basically, in the beginning, you started with 13.8 grams, and we had to calculate the Kc, the value of Kc, the value of Kp, and the partial pressures of all of them in equilibrium. So from the question itself, it can be, you can try and understand that we need to calculate the partial pressures, which means this is more partial pressure related and not concentration related. So using the formula PV equals to nRT, we were able to calculate the initial pressure of N2O4, and using the whole, X being the decrease in pressure as that the reaction approaches equilibrium of N2O4, we were able to calculate the value of X because we were given the pressure at equilibrium as 9.15 bar. And we first calculated the value of X, and then we calculated the partial pressures of N2O4 and NO2. From this, we were able to calculate the value of Kp, and Kp and Kc are related in such a way that Kp equals to Kc into RT to the power delta N, where delta N is the subtraction of the number of moles of the products minus that of the reactants. And from there, we were able to calculate the value of Kc as well. So for such questions, the one thing I would say is read the question, take it in, and then start solving. It's okay if you do not get an idea as to what you need to do immediately. If you still find it really difficult to, try and solve it, then you can always come back to it. But the one thing that I would always suggest is make a list of the things that have been given to you and the list of things that you need. Usually the clue to solve the problem is there, because here we had the partial pressure question. That in itself is an indication that we need to use the pressure and not the concentration to solve this question. And with that, we're done with question number 7.8. In the next video, we'll be discussing, I believe we'll be talking about how Gibbs energy and equilibrium constants are related. It's the next topic that we're going to be talking about.